speaking for food processors in general is Sam Mason of Tillamook Cheese in Tillamook, Oregon, where you can be a few blocks away playing on the beach, but the cows are still back at the ranch, hard at work. The neutral perspective of a consultant is provided by Dan Burgard of Cascade Earth Sciences. When people in western Idaho or eastern Washington say they're going to town, they mean Spokane, where there's never a dull moment. So with that, let's bring our panelists on. And gentlemen, Dan and Sam, can you pop up your cameras and let's get going. Excellent. So this is our Situation and Trends panel. Sam, can I hear you, or are you muted?
I was muted. Sorry about that.
There we go. And Dan, can we hear you?
Yeah, I'm here.
How are you gentlemen doing? I see it's warm and sunny in Spokane today. Is that right?
Well, cool and sunny.
Cool and sunny,
but sunny is the key.
And Sam, it looks like there's sun on the beach out there in Tillamook. Is that right?
It's a little bit drizzly. It's a typical winter weather for Tillamook, Oregon right now.
Okay. Well, listen, I want to do a little housekeeping for our audience. I know that I was on mute when I first talked at the top of the hour. We got that corrected. We like to have folks dial in by telephone because it's a reliable antique technology and it always works. But if you want to listen on your PC speaker, that's fine too. That works. Might be easier for you, but don't do both because you'll get an echo if you do that. So with that housekeeping comment, we want to thank Sam from Tillamook Cheese and Dan from CES. We're going to run through the topics that the panel is going to be going through, a couple of them, and we'll bring on the first presenter, and then we'll have the panel come back and join us several times over the course of the next couple hours. But the topics we want the panel to focus on is Sam, who's really in business. We want to hear what his challenges are at Tillamook. Dan, the consultant, we're going to have him give a perspective about challenges across other segments of food processing and other industrial segments. Both of them are going to share some disaster stories of attempts at remediation gone badly, and on the other hand, some success stories. And we'll follow that up with a discussion of where is the most bang for the buck? What's the least amount of dollars you can spend to get the most benefit? And finally, for smaller, mid-sized, smaller manufacturers, the question is, how big do I have to be? What kind of flow rate per day? And what kind of personnel do I need? So that's where we're going. We certainly welcome your questions during the panel and during the presenters as well. All you have to do is click. There's a chat screen. We'll be watching that. If you got a question, we'll ask the panel on your behalf. So let's start. Sam, you're the environmental manager for Tillamook Creamery Association. Is that right?
Yes, I am. And we've been in business since 1909, so a lot of people in the Northwest know Tillamook Cheese and Tillamook Ice Cream, and for anybody else, you ought to give it a try. One of our challenges is that as a dairy manufacturer, we do have wastewater issues that have to be addressed. We actually discharge our treated wastewater to a salmon stream, the Wilson River, which is a very high-quality river in the Tillamook area. So we receive not just the wastewater from cheese manufacturing, but also from ice cream and dry powdered whey manufacturing. In addition to that, we operate a visitor center that is the #2 tourist attraction in the state of Oregon. So when they built our plant, we were far enough from the city that we didn't have a sanitary sewer. So we not only manage industrial wastewater, but also sanitary waste as well. So that's a challenge for us.
So what's your biggest problem? I mean, you've been around for 109 years. You haven't solved your problems yet. What's the biggest problem?
As a problem of being here for a while, we have aged equipment that is overused and undersized for the current challenges today. So we've had some issues with our wastewater meeting the challenge of treating the water in the quality that's required to discharge directly.
So in your case,
right now,
we really don't have time for you to describe your entire plant and how it works and what you've done, but just tell us what's the next thing that you would like to do to your plant.
We're very concerned about the presence of butter, fats, oils, and greases in our wastewater that cause difficulty in the aerobic treatment process. So we're going to be addressing that in the next 6 to 12 months.
So if you had Dan come down pro bono for a couple of days, what would you want him to do with you as a consultant?
As much as, and I know Dan real well, he could help us quite a bit. We've actually hired a consulting firm to provide us with engineering solutions to our problems.
Okay, so Dan, what's the first thing you'd do with Sam if you were there?
Well, the first thing would be to take a look at the water quality, what the challenges are with the fats, oils, and grease, where they're coming from, and what the best options were to put an integrated system together that would solve the problem, not only just at the point of discharge, but in terms of how it all integrates with the treatment processes and their needs for clean water to discharge to the river.
Okay, let's go on and ask Dan. I mean, based on what you know about SAM and dairy, how many of the challenges that Sam's looking at right now are the same challenges everybody across all segments is looking at, versus what's unique to a dairy?
Well, some of the things unique to a dairy would be the high nutrient content in the fats, oils, and greases that they have to deal with. But that's not, okay, I said it's unique, but that is a challenge with any animal product processing operation, where you've got dairy, where you've got meat. Vegetable processors who cook and fry have oil and grease issues. There are suspended solids issues with the other vegetable processors. Other types of operations just need to clean the suspended solids out of their water to avoid plugging. If they want to reuse the water in the plant to try to conserve and reuse that valuable resource that is the water, it's an expense and it is a dwindling resource that we have. Reusing in the plant is important, and solids removal or filtration of the various processes is critical to that reuse step.
So, okay, we have 3 presenters coming up shortly, and I'd just like to ask you generally, as a educated audience yourselves, the two of you, an educated audience, what are you looking for from these presenters? What do you want from them?
Well, one of the key things is to understand, first of all, that their products will actually solve the issues that we have. For instance, fats, oils, and greases are things that could be present and cause some disruptions of certain filtration systems, so you may have to remove that first. It's kind of a stepwise process to take away, the gloves and the sticks and the large objects, and then follow that by a finer screen, the pits and the walnuts and things like that, to get to a smaller size that can be handled by the fine mesh screens that are available. Okay, and Dan, how about you? What are you looking for? I mean, just in a generic sense, when you sit down with a supplier, what do you want from that guy?
Again, like Sam said, some of the is it going to work, and where does it fit in the overall treatment process? What has to come before it? What has to come after it? What is the operation and maintenance complexity? How do you have to have a trained operator run it? How expensive is it to operate? And what is the efficiency to expect from the process? Yep.
And then just for speaking for myself, the thing I always like to ask somebody is, okay, what's new? If I saw you 3 years ago, is it the same presentation? If I see you 12 months from now, will it be a different presentation? What's new? Where's it going? What's next? Is this the right time? Those are the kinds of questions I want to be asking as well. So we're sort of acting as the proxy for our audience because chat is slow. But here is some feedback we got from folks as they registered. And let's take a look at this just as the panel before we get the presenters out here. We asked folks, what are you filtering for? Everybody's filtering for solids, but almost half are filtering for fog. Is this a typical breakdown of activities, or is this are we skewed one way or the other based on what you're seeing? It all depends on what your actual permit says, but this is very typical. You have to reduce TSS below
a particular limit that's either on your ultimate discharge or perhaps your discharge that goes to the municipality. And fats, oils, and grease is also a big component of the things that have to be removed.
Okay. We also asked what topics of interest you have for the panel. This is for you guys. Reducing BODs and addressing the cost and fog seem to be tied for first. Again, any comments? Did this reveal anything to you about how we should vector the presenters today?
This is typical from a standpoint of the treatment process. The fats, oils, and greases are a particular challenge because they float and they don't particularly lend themselves to easy treatment in a biological process. They clog up membranes. Reducing the BOD is a treatment process expectation, and suspended solids, again, is critical for reuse and for discharge.
Skip, are you on mute?
Oops, I was muted. Sorry. Did you have any comment on that prior slide?
Oh, I like this slide because it shows that there are members of the audience that really do need something right away, as is the case for us.
Right. So I think what's cool about this, or the takeaway from this slide, is that, you know, about 25% of the audience needs something done right now, but 75% or better is really, really interested, with only a few future tire kickers in the audience. So with that, let's, oh, I'm sorry, one more slide. Obstacles to deployment, capital availability, and I would combine that with it just doesn't pencil out for us yet. Almost half the audience. But then a tie at 25% for, gee, we really don't really understand the process well enough to make a decision, and I want a whole lot more information about the products available. So I'm feeling pretty good about that because this audience is going to benefit from what the presenters bring us. Do you have any other final thoughts about the whole array of market segments or segments of food processing? We have paper and pulp in there because we do have some paper and pulp folks on, and you know, it's a crop. It's kind of like a big vegetable. Any other thoughts about how to attend to all of these different segments of the audience?
Well, I know that when you're dealing with wastewater, you first have to take away the large objects and then get smaller and smaller until you get to the fine particulate at the very end. And as you get to finer particulate removal, you also have to be careful not to have something that damages those elements, whether it's a membrane or a filtration process, to keep them from clogging up, things of that nature.
Well, I know that pulp and paper has particular issues with very fibrous materials in the suspended solids that tend to plug up filtration systems. And juice and beverage is often very soluble materials that they're trying to remove and don't lend themselves well to classical filtration that you would typically see, screening or just even filter media.
Well, great. The presenters are in the background listening to all this, so they'll be folding these, responding to these comments in their remarks. Couple of housekeeping issues before we get going. This will go really fast. We do this once a month, and as we looked at the audience's concerns, we decided to focus on suspended solids. All these manufacturers, all the vendors that we're going to see, do address dissolved solids. Some of them might mention that, but we're focused really mostly on suspended solids today. And for future events, if you've got a topic idea, we certainly want to hear it. So we'll pop you an evaluation URL. If you got a topic you want treated in this format, please do let us know about that. Just click and enter it in on the evaluation. So it's time for a time check. Keep things flowing. I think we're about 90 seconds long right now. We should be getting Cliff Callow in from GE. Cliff, can you join us? And we want to thank our panel, Don't Go Away panel, because we want to talk to Cliff a little bit as he arrives. Cliff, are you with us? Here he comes. And do we have sound for Cliff? I think, do we have Cliff muted? Cliff, I think you're muted.
You're absolutely correct, Skip.
Here we go. Cool.
Hello,
all right.
Happy to be here and look forward to presenting some solutions for you guys.
So, Cliff, as you've prepared yourself for this and you've listened to the comments, any particular thing you are excited to share with us? Just give us the highlight of what's coming.
Yeah, I think I've been doing this for 40 years, and I wish I said I started out of high school, but I didn't. But a lot of times in waste treatment and seeing hundreds and hundreds of plants over the years, people tend to overlook some of the simple, elegant, robust technologies. They put everything at the end of the plant, and it's just big, complicated thing to deal with. So look forward to showing you the high flow Z's, some of our spiral wound membrane cartridge technology. G has a large portfolio of soup to nuts technologies, all that address all these problems on a small scale, on a larger scale. So I look forward to presenting those to you.
Great. Dan and Sam, any things about GE and their products that you particularly want to hear about?
Well, I'd certainly like to hear about things like what kind of pre-treatment is needed, where do these technologies fit within the treatment stream, whether they're upstream for reuse or downstream in the treatment process before discharge, and what is the operation and maintenance considerations and difficulty of use.
Good question.
Sam, anything?
And I'll second that one of the first thing is the actual installation cost and the construction cost, but then even more important is the operation and maintenance, utility, consumption, things of that nature too.
You'll see, because of the breadth, Sam, of my presentation, we're not going to get into specifics like that, but certainly if you have a project, we can quickly show you. We have thousands of systems of different types all over the world and can address those questions quickly.
Great. And Cliff, I've got a final question for you before we let you into your slides and your videos. By the way, everybody, he's got videos. These presenters all have really cool, instructive videos, so it's not just going to be death by slides. But Cliff, I got a question for you. We're all about emerging technology here, and your company's like 150-something years old, and light bulbs and stuff like that. So how did you come about being an emerging technology business unit?
Well, it started back when GE went through the Jack Welch years and transformed from heavy industry, aircraft engine, and appliance industry into a well-diversified company. And the GE spirit of innovation lives on. In the early 90s, I'll go through the timeline. But GE purchased some of the premier water and water equipment companies, which I'll be talking about. And they continue to put a lot of R&D. We'll hear about new products, new innovations that save time, that save energy, that are elegant solutions, well thought out for a global industrial clientele.
Great. Okay. Well, let's let you take your show away, and we'll turn our cameras off and leave the stage to you.
Okay, so we're going to talk today about, again, this is a very broad presentation because I think that's a good place to start. So we're going to talk about removing dissolved and undissolved solids. And a lot of times when people look at problems, they don't spend enough time defining and measuring what the actual problem is, so it's hard to solve. So we're kind of touching this. And these are all methodologies that I've learned over the years from successes and the things that were not so successful. So I want to thank my friends at Emerging Technology Innovators for inviting me to this event. Very happy to be here. Just to touch on Ron's question about how did GE get into the water business. If you look at this slide, you'll see a lot of the name brands. You folks, many of you have been in this country, in this water environment for years and years. Companies like Xenon, companies like Betts Dearborn, Osmonics, Ionics. So we're built on a history of innovation. Xenon began hollow fiber UF back in the 80s. Osmonics was very key in development of spiral wound membranes, removal of dissolved solids. Betts was is a premier chemical water treatment company, so boiler, cooling, water, and waste technology. So the chemistry always enhances the equipment, right? It makes it work better. And so we all came together. I was a Betts person. I was started investing in the mid-'80s. In 2002, GE acquired Betts as a foundation of the water business. They subsequently went on to buy Osmonics in 2003. 2005, they bought Ionix, a well-known Massachusetts company, highly engineered systems, large desalination plants worldwide. Also Ecolochem out in Norfolk, which was mobile water. And then the crowning jewel, so this gave us the whole spectrum of portfolio from clean water, filtration to wastewater processing and reuse when they purchased Xenon in 2006. So I belong to a group called the Indirect Group, and what that means is we go to market using carefully selected third-party companies throughout North America. These companies are local to you guys. You probably already work with them. They're a combination of OEMs that build equipment and provide solutions, distributors that have our technology in the shelf in terms of filtration, consumables, that sort of thing. We're value-added resellers that do part of the service piece as well. So all these companies allow us to bring solutions to you quickly with companies that are local to you. Often these small businesses are second and third generation. So it's very rewarding for me. So I have quite a large territory to cover. I have specialists that help me in doing that. I have equipment specialists. I have membrane specialists, filtration specialists. We also have a great inside team, great customer care team, aftermarket parts sales for our equipment and consumables, and then an overall technical support numbers that anybody can call, the number or the team mailbox, and look for a solution. So my team covers North America with this network of third-party companies. There's 8 account executives like myself, 4 specialists, and 2 team leaders. Okay, now we're going to get started in talking about dissolved and undissolved solvents. And again, before we can solve a problem, we're going to have to define what we're trying to do on a basis that we can measure it. So we have undissolved particles and dissolved particles. Questions you want to ask yourself is what is the stability of the particles in the stream? This would be undissolved particles. For dissolved particles, what are the saturation limits of the components? Will the water support biological growth, which is the bane of many processes, with microbiological fouling? And will the water at any point in its evolution from non-usable to usable cause corrosion? So we talk about undissolved, which would be particulates. We've all seen, in a glass of iced tea, we put too much sugar in it, all the particles drop out of the bottom. The particles can also be contaminants such as chip scale, silt, as an example. Then we have in the dissolved world, different minerals. So we have organic, inorganic components. Inorganic, being your metals, your calciums, your magnesiums, your sodiums, and so forth, and then the organics, which would come from nature, like the cells in our body. So it'd be a hydrocarbon chain with some kind of a radical on it, and typically the origin would be plant material has fallen into a surface water, hydrocarbon that may have been a contaminant from an industrial process. So between these are all in dissolved. And then, they transcend between being dissolved and undissolved. So everything has a saturation limit, as we all know. So again, we're trying to just familiarize you guys with the terms that we want to do to measure the problem. Back into the particulate, the undissolved materials, are they settlable or are they non-settlable? There's a lot of people have a lot of interest in removing fats, oils, and greases. So, the first question is, well, does it float? Does it sink by gravity? Because that makes that leads you towards the type of solution. If it's a non-settleable, non-dissolved particle, it could be, simply like a 1 micron silt that you're trying to remove, or it could be a more complex, like a colloid, or probably the most complex is an emulsion of either oil and water or water and oil. And then last, again, will the water at any point in its evolution from clean to reusable support microbiological growth? These are all the things we need to understand about what we're working with in order to design a solution. Part of looking at a problem, and I learned this when I was at Toyota for a few years, you really want to define the problem in terms of a black box. What are all the inputs? What are all the outputs? And the black box concept helps us really define, what is this problem really costing us? What is it worth to solve? So it leads into the business case, because one of the big inputs and outputs always has to do with commercial constraints. Where does the money come from? Where does it go? Could we possibly take something that's a waste product now and reuse it? If we make it more consistent as a waste product, can we reuse it? So variability is a big thing you're looking at when you're laying out and developing a project. And again, the first step is getting some data. What are you trying to solve? Some pilot information or some trial information, and then getting funding for the project. You'll see a lot of the solutions I'll be talking about in my slideshow are fairly simple, so they're easy to implement. It's not a large capital project, so I think you'll be happy with that aspect of it. I wanted to familiarize everybody with some more terminology. So this is the filtration spectrum. It's a classic osmotic slide. It's been around for years, so we're going to have some fun with it today. So what it does is, when we talk about non-dissolved particles, we want to define the size. And this goes going from right to left, relating it to things that we're all familiar with, in the natural world. How big are they? So we talk about micrometers or microns. So filtration pore size is usually expressed as microns for undissolved particulates. When you get down into the dissolved materials, you're going to look at them in terms of molecular weight. So think of a molecule, think of a hydrocarbon chain, and so forth. So as some good examples, we're all familiar with the size of beach sand, milled flour, how big a human hair is, and the technology to remove those would be some sort of particle filtration. We'll be talking about depth filtration later on. We'll also be talking about hollow fiber UF. And then things that are smaller. So we see that the size of indigo blue, like the dye they use in manufacturing blue jeans and towels and so forth. Those sorts of dyes, they're in the 5 micron range. You can see on the scale up there. And the technology to remove those would be microfiltration. Going even smaller for removal, gelatins, starches, powders, viruses, if you're familiar with that in the food industry, that would be in the realm of removal by ultrafiltration. And that's a key thing for ultrafiltration, because the pore size will remove viruses, cysts. So most of the drinking water plants worldwide have some sort of a ultrafiltration as a final step. Now we get into things that are fully dissolved, like a sugar solution, for example. And a larger molecule like a sugar would be primed for nanofiltration. The nanofiltration and the reverse osmosis are available in the spiral wound membrane format that I'll talk about in a bit. And then the smaller molecules like sodium chloride, all your aqueous salts, metal ions that we're familiar with as contaminants in water, dissolved iron, that they are all removed by reverse osmosis. Reverse osmosis takes out, nominally 95 to 99% of everything. So if you have water with a TDS or conductivity, however you're measuring it, you're going to take 99% of that value as a pure product. In all these membrane separations, we're not really removing it. We're just moving it around, if you will. So we don't destroy it. We're just using that positive membrane barrier to separate it. Important part of measuring is lab work. So I want to familiarize people with the particle size analysis. You can read some of the details here. Particle size analysis, will show you quantitatively what's the size, how many particles you have to deal with, so you can design your filtration around that. Particle volume is important. We're going to see, and we talk about melt-blown polypropylene depth filters, how the void space is really important for filter performance. So here's this is a typical part of a report on a particle size analysis done in a laboratory. This was done in our GE Woodlands laboratory in Texas. So it shows that across the whole range of particles that were present, you had the volume in cubic microns, if you will, the particle range in microns. But what we really want to draw this is that in the 20 to 30 microns are most of the volume of your particles. So that means that that 20 to 30 micron range is going to use up most of the dirt holding capacity, right, in your depth filtration. And we're going to revisit these topics as we go through the slideshow. I'm just kind of building. Another part of the particle size analysis would be the tabular format. So it gives the range of micron sizes in the sample of raw water in this case. And then we see in the 1 to 2 micron range, we had almost 7,000 parts per milliliter, and that was 26.8%. Looking at these two slides, we would say, well, we want to remove everything above 1 micron, bigger than 1 micron. But we're going to have enough dirt holding capacity to deal with the 20 to 30 micron range, which is where most of the volume is.
Hey, Cliff, this is Skip jumping in. I just want to let you know that we're running the clock down, and if you can, this is great stuff, but you need to accelerate to your product and solution, otherwise we will run out of time for you.
Thank you, Skip. So we're going to talk about depth filtration. It comes in a cartridge format. There's all different lengths, end adaptions, and so forth. This is a GE Osmonics Heritage product line, made in America. All the certifications that are needed for food, NSF. We work with the polypropylene suppliers for the purest of materials. So GE is known for its very high quality and good value. Before I go into how melt-blown polypropylene filters work, I just wanted to show you guys how they're made. So it's kind of like cotton candy. We all see cotton candies growing up as kids. So it's molten polypropylene formed into a log on a mandrel that's spinning at a slow speed. At the top you see the heads. So these are computer-controlled heads. They're streaming out molten threads of polypropylene and developing a filter matrix along this log that's on a rotating mandrel. And why do we care? Because it all translates into dirt holding capacity. In depth filters, the term graded density is important. So in depth filtration, we're using the whole working radius of the filter, ideally, to remove dirt. And if the voids are larger on the outside and smaller on the inside, they're going to last a lot longer. So in this slide, we see that because of the manufacturing process, the GE Hydrex is a graded density, and you'll notice that we've used almost the whole radius of the filter, where the one on the left is less expensive to make, so therefore the cost per filter is less, but the use per filter is going to be double what it is the graded density. So the Hytrex was invented by Osmonics in the early 80s, again, an example of innovation. You can see on the slides that at all the, because this is not a graded density filter, all the particulate segregated into one layer, so you've wasted probably like 2/3 of your filter. Whereas on the Hytrex, you've utilized all the filter. So again, and we have lots of data on this, that graded density will last twice as long as non-graded density. So when you're looking at something, obviously you want to look at the yearly cost of ownership, including, you know, how long does it take to change it, what's the disposal cost, all those things. Then we go into a patented Z-Plex technology that came out in the 90s. You know, you saw how they were manufactured. As computer-controlled equipment became more sophisticated, we were able to develop this technology. So Z-Plex gives it's like super graded density. It has strands are smaller. It's made in the same way. So on the left we see a typical conventional melt blown polypropylene filter, and then on the right we see Z-Plex. So you're going to see that the fibers are thinner, the void space is larger. So for the same, you know, cubic inch, if you will, of depth filter, these fine filters give you, you know, a much more graded, larger void area. You're going to get half the pressure drop, which is important. Pressure drop translates into energy costs, right? It's pumping costs. So there's a big advantage there. So these I call these super graded densities. So GE Z-Plex technology, super graded density will last twice as long as a Hytrex graded density that we came out with in the 80s, and 4 times as long as a non-graded density filter. That's a really important statistic to remember for you know, the business case of what we're trying to accomplish. Now, the newest family in our depth filters is the large format high flow Z. So we've taken that Z-Plex technology in a large format filter. And large format means these filters are 6.5 inches in diameter and 40 inches long, and nominally handle 100 GPM. Most cartridge filters that everybody's familiar with, are 2.5 inches in diameter. There's a lot of advantage to this large format. We did not come out with the first large format, but we've come up with the best large format, as you'll see in a minute. So the high flow Z uses the Z-Plex technology in a large format configuration, where the competitors' designs are all some sort of a pleated design. So the pleated, you know, would capture dirt on the surface. It doesn't have that graded density of void space that we would see in the depth filters. And there's nothing like this on the market. We have tons of case history we've done in many industries, including food. This is the tool of choice for you know, removal of fat particles, deformable particles like gels, you know, particles of vegetables and fruits, and you know, we're looking at you know, how are we going to implement reusing this water, cleaning this water up. You know, point of use. You know, let's before we mix it all together, let's try to do it at where we're, you know, washing the vegetables or washing the fruits or concentrating the juice. You know, so it's simple technology. Another advantage of the large format, it's in a horizontal housing, so it's very easy for it's very operator friendly. All right. The handle is specially designed. It's ergonomic. It's easy to open. It's easy to look in. It's just a very a nice operator-friendly configuration. Here's some examples of why this large format is a great solution for plants. So here we have an example, both 400 gallons per minute, right? So we could do that with 4 rounds, and there are 4 high flow Z large format cartridges in a housing versus 20 rounds of 2.5 inch. If anybody's ever changed out a 20 round filter housing, it's a lot of work. Operators are not happy about it. It's certainly not horizontal. It's a big deal. There's a lot of room for error in sealing. A filter is only as good as the seal at the bottom. So this is for the same flow rate, 400 GPM, 20 round versus 4 round. You decide which technology you'd like to have in your plant. So it really gives you 5 times the flow rate as a 20 round. Dirt holding capacity, again, that's really where the business case is made. What's the filter life? What's the dirt holding capacity? All these are ASTM tests, and we have lab tests we can test, an incumbent filter manufacturer be using. So in this example, again, the same flow rate. So we have the 40-inch high flow Z can hold 15 pounds of particulate, and that would be the equivalent of 5 2.5-inch things at 2.6 pounds per cartridge. That's 6 times the dirt holding capacity. I want to transition now into the removal of dissolved materials with spiral wound membrane elements. And we're going to come back to this slide. It's called spiral wound because it utilizes about 350 to 400 square feet of active membrane area. And the membrane is what does the work, as you'll see in the animation we're going to do in a minute, into a spiral format. So here's a typical cartridge simulating how it would look in a housing. So from the right, the feed solution goes in. You can see the particles concentrated. On the other side, you'll see that the pure water comes out. So if we do a cross section here, we see the feed spacer, where we have the dirty side of the membrane, the clean water membrane. And spirals are available not only as RO, but also as nanofiltration, ultrafiltration, and microfiltration.
Skip, you're on mute.
Hey, Cliff, you can see I just jumped on the screen, and I'm going to ask the panelists to join us right now so we can engage the panel with you. So go ahead with your presentation, but just in the interest of time, I'm going to have those guys join early. So Dan and Sam, turn those cameras on, and go ahead, Cliff, take it away.
Okay, so again, we're talking about spiral wound elements. We talked about that in so here's a typical, this is be a reverse osmosis machine. So these elements are loaded into housings. You'll have a pressurization pump. For pretreatment, you'll have cartridge filtration in a housing. So everybody's seen these types of machines in their plants. G is single source, so we make the membranes, we make the filters, we make the pumps, we make the equipment. So it's single source accountability. That was a part of our animation. This I want to transition into the hollow fiber UF. This is kind of the heavy lifting technology. This would be more towards the capital equipment side of things. And you'll see how we go from a porous membrane into a lumen and into a module. This is a G-xenon technology. So we have, again, a very robust membrane. It's about the size of a piece of spaghetti. You have the contaminants on the outside. The pure water is on the inside. Pore size is 0.02, so it's going to remove viruses, cysts, bacteria, which is an important attribute.
Cliff, I'm going to have to jump in because we are going to fall behind schedule. I want to ask Sam and Dan what sort of questions they have for you, but before we get going, how many more slides do you have to go before you're at your preferred stopping point?
I think 2 or 3, Andy.
Can you do the 2 or 3 in under 30 seconds?
Sure.
Okay.
So here's what a module looks like. The key things, it's PVDS, so it's chlorine tolerant. We came out with a 600 square foot version of this recently. Transmembrane pressure, so it's 40 psi and below, so it's a fairly low pressure operating system, which translates into lower cost. If you quickly do the animation, and the picture tells the whole story. So in a machine, it's the hollow fiber UF. Outside in, you see the particularly building up on the outside, the filter cake, you see the air scouring. Then you'll see we'll go through a cycle of back pulse. Now we're reversing the flow, so we're using some of the filtrate to the backflow, back pulse, blow off the filter bed, and start the cycle over again. So hollow fiber UF, again, it's a capital equipment play. You're going to see it, more as a retrofit to a clarifier. That's the classic, area where it's put in. The new system could be part of a membrane bioreactor, and there's a lot of different ways to use it, but it's usually a larger thing. So you go from the lumen, the hollow fiber, into the module. The modules are built into racks, and you can have a number of different racks. So my last slide, you'd see something like this.
Okay.
PVDs, again, where you've got to remove heavy solids. So not only food clarification, but mining, CPI, power, cooling tower, filtration is what you're looking at.
Okay, we're gonna have to jump in, and we do have a couple questions from the audience, but let's start with Sam and Dan. Any questions you have that jump out for Cliff? And Andy, can you put us in a full screen mode, please? Excellent. Sam, Dan, what have you got for Cliff?
Yeah, Cliff, I did want to ask a question. It's repeating really what Chris Carey had asked, and that is some of the things that you presented are disposable cartridges, and other ones are clean-in-place type cartridges. So could you kind of talk about those real quick?
Yeah, I mean, again, I covered a big breadth of solutions, right? So the cartridge filtration is disposable, whereas the hollow fiber UF is part of a working system where you have a clean-in-place methodology. So again, you got to define what you're trying to do, and look at the whole cost picture. What can we reuse? Is there any BTU value to the the filters that are contaminated? Lots of can recover metals from the filters, but yeah, you did pick up on the distinction. So the spiral wound elements, which come in reverse osmosis, nano, micro, and ultrafiltration, that's a clean-in-place technology. The hollow fiber UF is a clean-in-place technology.
Great. So Dan, you got a question or two?
Yeah, I'd like to just forward on what some of the participants are asking, particularly in terms of what temperature ranges are on these depth filters, and what do you recommend for the reject?
That's a good question. There's actually two parts to that question. So most of the depth filters can go up into the 150 degrees F range. If we have cord filters that are going to push the higher end of the temperature limit, as opposed to non-cord. Again, they're made out of polypropylene. Plastic is deformable with temperature, so we go that direction. For the spiral wound membrane elements, 120 degrees F for typical pure water elements. We do have high temperature elements that can go up to 180 degrees F, continuous service. And the UF, you typically don't look at higher temperatures, so I'd have to guess it's probably like in the 150 degrees F range.
Okay, we seem to have another question about how best to remove sand from vegetable wash water. Any comments on that?
Yes, sand is a real easy one, and you see that a lot, sand and grit and stuff from vegetable washes. The High Flow Z, the classic depth filter, and again, if you go with the graded density and the super graded density, like the Z-Plex, you're going to get 4 times the filter life. So that's less downtime, less disposal costs, a lower cost of filtration for the year. And we put those in tons of intermediate steps in a food plant where they want to reuse rinse water, reuse wash water. It's got grit in it, it's got gels, it's got greases, deformable particles. Perfect fit for the Z-Plex technology.
Great. So, panel, let's use our audience feedback and see, have we addressed the topics well in this presentation, or is there something else that we should be asking Cliff to attend to the general audience, or are we okay?
I think one comment about the reject water. What is typically the solution for reject?
Good question. So, and I didn't touch on this, Dan, so I apologize. So, with membrane separation, we're moving things around. We're taking a dissolved impurity, we're concentrating it up on one side of the membrane, and we're making it more pure on the other side of the membrane. So the reject stream, which the water efficiency of these systems is typically, from the 75 to 90% range. We have brine concentration technology. We're using like a third machine is very common. A big drive in membranes is lower pressure, so more pure water for lower and or higher efficiency. And another issue is just how are we going to use it? So let's say you have a plant where you have a stream, you want to purify it up to a certain level, and you don't want to, business case, you only want to make it good enough to reuse. You don't have to make it perfect. So it doesn't have to be 99% pure, maybe just 50% pure. But maybe you can use the reject water, which would be, have the concentration of remove contaminants. As fire water, as utility water, as a wash water for something else. That's a typical methodology. You look at all these reuse scenarios. Okay, well, how good does it have to be to reuse it, and what can we do with what's rejected? And in the process side of food and other industries, they may be recovering, what's rejected from the membrane, and now you're looking for some other use for the purified.
Okay,
I have a question that has to do with pretreatment, and are some of the equipment that you're talking about, it could be affected by fats, oils, and grease, and we do have that. Some butter fat comes in with our wastewater at the dairy.
Yeah,
this is great stuff, guys, but we have to do short answers. Crisp, 3 words.
Yeah.
Okay.
Z-Plex. Yeah, the disposable Z-Plex. I mean, that's the tool of choice. It's going to solve a lot of you guys' problems.
Okay, we got to keep moving. So I'm not going to ask the question about have we covered all the interests of all the segments because we don't have time for it. Also, in this segment, we were going to have Sam and Dan, or Sam and Dave, or whatever your names are. We're going to do a disaster story and a success story, but we'll pick that up later down the show. So thank you, guys. Don't go away. Cliff, this was great. I am so sorry that we had to push you forward or push you along, but the time you spent or the efforts you spent to scope the problem before you got to your cool solutions was really good stuff. And I regret having to watch the clock, but thank you so much. And
I look to seeing you all again on other presentations. There's a lot of good solutions.
We'd love it. It's good stuff. Thanks so much. We do have to do a time check. We are well over 5 minutes over, so we're going to have to get crisper and punchier. Right now, Sam, Dan, please do stick around, but I need to tell folks why, well, actually, who OMAP is and why they're sponsoring this.